Got it. Should disappear. Yeah.
All right, hello everybody. Welcome to this week's Grasp on Robotics seminar. I am Cynthia Sung. It's my pleasure today to welcome our speaker, who I'll be introducing in a minute. Before we get started, a couple of reminders. One is that you can find all of our previous talks on our website and our YouTube. For today, we will be having both in-person and broadcasting over Zoom. If you are joining us over Zoom, you can ask questions through the Q&A button at the bottom of the screen, and our wonderful panelists, Shivangi Misra and Wei-Shi Chen, will be monitoring the chat to be able to bring up the questions in the room. If you are in person, of course, you should feel free to raise your hand and you can ask your question in person. If you are in person, then please do wait for one of the panelists to bring you a mic so that the people who are on Zoom can hear you, and we'll go from there. So with that, it's my great pleasure to welcome today Professor Nick Gravish. Nick Gravish is an associate professor at the University of California in San Diego. He's in the Mechanical and Aerospace Engineering Department and also a member of the Contextual Robotics Institute. Professor Gravish did his PhD at Georgia Tech in 2013. Afterwards, he did a postdoc at Harvard and then moved to San Diego, where he's now doing a lot of really interesting work in bioinspiration, biomechanics, and robotics in all sorts of domains, aerial, underwater, and most recently, sand. So he's received a number of awards, including the NSF Career, also is leading a NSF EFRI on soft robotics. And so we're really excited today to hear what he has to share with us. Please join me in welcoming him.
Amazing. Thank you so much. Can everybody hear me back there? Great. Thank you for the introduction, Cynthia. Thank you for the invite. I'm super excited to be here. I've got a couple quick plugs first. The first plug that I've got to do is if anybody needs to go and write the RoboSoft paper, the deadline is November 1st. You can leave if you have to. We're hosting RoboSoft at UCSD, at San Diego, sorry, not UCSD. I'm excited about this. November 1st, please get your submissions in. It's going to be a great conference. The first time RoboSoft's been in the United States since the founding of RoboSoft. I'm really excited to be here also to talk about the Contextual Robotics Institute. It's been around for 8 years, but 16 of us just recently moved into a beautiful new facility, the Franklin Antonio Hall building, 18,000 square foot facility. And I'm part of this cyber physical systems collaboratory, and it's really allowed for a lot of great collaborations and interesting work. So sort of 2 plugs for San Diego. If anybody's in the area, please reach out to me. So today I want to talk about adaptive systems, and specifically adaptive systems through compliance, dynamics, and contact. My lab works to create multifunctional systems, multifunctional robots, and adaptive robots, and I'm particularly interested in structures, mechanisms, and dynamical systems. Something I want to be honest with you all for a second here. Cynthia said my CV, a PhD at Georgia Tech and a postdoc at Harvard. I've actually never taken a mechanical engineering course in my life. My degrees were in physics, and you might see that sort of infused through the way that I approach these problems. I'm really interested in distilling representations of these complicated systems down to their simplest elements and studying them at the sort of simplest level of representation that we can. And so just to give some sense of what I mean, so I'm interested in systems that have some sort of compliance that allow them to adapt to perturbations from the external environment through structural changes, through changes in compliance or changes in reconfiguration of body type. I'm interested in systems that have dynamics that allow them to have interesting adaptive properties through sort of dynamics that can be at the structural level or at the feedback control level. And I'm also interested in collective systems, and particularly the collective systems that interact through contact, that can make contact with each other and make and break contact with each other, and how we can use that sort of the interesting physics of contact interactions to kind of control collective behaviors and make for interesting adaptive collective behaviors. So my talk is organized in these three different parts. I first want to start with talking about how we can think about structural mechanics as modulating and allowing for adaptive behaviors. And I'm going to talk about a particular type of structural mechanics here, which is the mechanics of curved planar structures. Curved planar structures are very interesting because if you take a flat sheet of paper, you can bend it in many directions. If I put a curve in that flat sheet of paper, now I have a direction of strength associated with that flat sheet of paper. Tubes have the same kind of structural property that if I take a tube is quite strong to transverse loads, but if I put a pinch in that tube, I create a local flexible joint, and I can create flexibility on demand within those structures. And so I want to talk about how we can think about using these kinds of tubular structures to make reconfigurable soft linkage robots, and using virtual internal joints to change the kind of kinematics of that tubular structure, so that we can think of these as kind of like hybrid soft rigid robots. They have the kind of softness because they're inherently going to be made out of soft materials, but they'll have the sort of rigidity associated, or the kinematics associated with sort of more traditional linkage-based robots. And these kinds of devices might have many applications in terms of reconfigurable locomotion systems, robot arms in which just a few number of degrees of freedom can still achieve high levels of manipulability for lightweight applications or deployable applications, things like that. But it all stems from this idea that I introduced before, that if I take a paper roll tube and I put a pinch in it, I can create basically a local flexible joint. And so a paper roll tube is, the example that we started with when we were thinking about this. But it's kind of hard to kind of like functionalize a paper roll tube. How do you then create that joint in a specific location? How do you move that joint around? How do I actuate that joint? This is a path of research that we've been interested in for a while now, and have explored many different ways in which we can achieve this kind of reconfiguration of these flexible pinch joints. The first mechanism that we were interested in looking at was using vacuum pinching. If I take like a elastic tube and I just pull a vacuum, it's going to pinch. It's going to pinch somewhere along the length of that tube. So if I want to control where it pinches, I can put a little eccentric circle that basically puts a pinch in that tube, and it creates then a controllable location of that flexible joint. So now, just by vacuum pinching and controlling the sort of eccentricity of that shape, I can control where one of these joints might be created. We can do this with these vacuum tubes. We can create sort of analogs of very simple rotational pivot joints. You can see these rotational pivot joints, when they're loaded along the direction of their motion, they bend freely. When they're loaded off that direction of motion, they'll support some load. And then we can make two-link and multi-link versions of these. This is just showing two cases where the rotational pivots are aligned, and a case where the rotational pivots are not aligned. And this was really interesting. We can now create along a tube specific locations where we create joints. This is completely repeatable. We can always reconfigure these joints. But the problem with this approach of creating reconfigurable serial linkages using vacuum to create that pinch joint is that the strength of that link, if you will, is dictated purely by the material properties of the material you use, right? So like I have to use a soft material because I have to be able to pinch it. But the softness of that material, once I've pulled that vacuum, it's the only thing that's keeping it from buckling. So if I want to make a strong manipulator, then I need to find the right material that is both capable of supporting loads as a link, but also not buckling under just the external loads. And pulling a vacuum already sort of weakens it to want to buckle. So we took the opposite perspective, and we looked at positive pressure pinching. It's basically the same idea, except now instead of applying a pinch that buckles the material through this eccentricity, we have to physically put some kind of device in there to create this pinch. And so the device we put in there is just literally like a 3D printed little rod. You put a 3D printed rod, you inflate this balloon. The columnar link structure of that is very strong, and the strength of that is dependent on the pressure. If I just increase the pressure and I have enough material that can support high pressure, I can make very strong linkages. And yet, by creating this cross section that isn't circular, it's very flat, I can always maintain this flexibility at that location. So this sort of solves the problem of not having to worry about the material selection. As long as I have a material that can support high pressures, I can create columns and links that have the strength that I want. So from this, we propose this idea of basically taking inflatables, like an inflatable beam here, where I can create locally pinches within that material or within that column. And those pinches create joints, except the question of then how do you create the pinch and how do you create the joint? We had to address that. And so our idea was basically to now use effectively just a simple rotational joint like you might find in a robot arm. However, this is a special rotational joint that can move along the length and translate to different locations within this tube. So these are individual modules. They have their own batteries. They're actually 2 sets of batteries and microcontrollers on the left and right side. You can't have cables running through this thing because it can rotate the rotation axis 360 degrees or continuously. And then this module can move within the tubes by moving along a chain that's contained in the tube. The chain is literally just like a pull chain that you might find for like a fan or something like that. So we take these rigid internal modules, we put them inside this like soft tube. The tube is inflated, so it's got some structural properties to it. And now we can achieve this sort of combination of reconfigurable kinematic structures that have, relatively traditional kinematics. We've compared through OptiTrack measurements and sort of predictions, and we can make them then reconfigure their shape on demand. This is just an example of this. This is all sort of, I don't know, all these remnants of COVID research, seeing people's masks and things like that. This is work we did outside with deploying just one of these links. And so we inflate the tube, we move the link to the location that or the joint, excuse me, joint to the location that we want to form a joint. We create a pinch. We, in this current incarnation, have to depressurize a little bit to create the pinch. And then from that, we can actuate this just as we would actuate a simple 2-link system. And so this is just showing this joint moving to different locations. And so this combination of kind of flexibility from the flexible materials, the strength through the internal pressurization and the reconfigurability allow for a lot of interesting kind of adaptive type behaviors in these systems. One of the ones that we were really interested to explore was actually moving beyond thinking about like manipulator systems and instead looking at locomotion. And so here's about a 1.5 meter long version of this with 2 joints within it. The joint axes are off axis from each other. And so a simple just sweep of each of the joint axes leads to a locomotion gate. And you can get a lot of very interesting locomotion gates out of this just by modulating the location of the joints and the axes of the joints, which we've studied in a manuscript that's in review right now. By changing the relative link lengths, you can change the direction that this is going to move. You can make it move straight, make it turn. And so we can achieve sort of a wide variety of locomotion movements, not by changing the control signals that we're sending to the motors, but just by changing the kinematics of the structure of the robot itself. And it's all sort of predicated on our ability to use these internal modules to change and reconfigure the internal shape or the sort of kinematic representation of the robot itself. So this has been really interesting and has been a fun example of the kind of evolution from starting from paper rolled tubes, thinking about vacuum systems that can produce pinches, to then moving on to these positive pressure inflated tubes. There are many more steps in the middle of that. But the ultimate result is, I think, a very interesting sort of combination of these rigid and soft systems that, again, through the reconfigurability, allow these robots to adapt to different locomotion challenges. The other example that I'm really excited to show in the context of mechanisms comes from tape measures. And I think maybe some people here are looking at tape measures currently or have thought about tape measures. It's one of the most fun structures to play with. We have a bunch of them in the lab. Tape measures have this really amazing property where you have a revolute joint that I can change the location of that joint on demand and move it continuously along the length of the tape. And then I've got a stiff member here that can support load. This is like vertically, this is a little bit of water. And so we're basically lifting this bottle of water. And so from this combination of regions that are stiff and can support high load, both along the length as well as transverse, We can also reconfigure the joints, and we have this combination of, once again, a kind of reconfigurable mechanism that can change its shape and apply forces to the world. And we've been working on this in the context of a simple kind of planar gripper here. So imagine just taking two sets of tape measures, putting a bend in it, and then going out and pushing on objects. And what you'll see is this specific mechanism provides a lot of really interesting manipulation kinematics, because now you don't just have two fingers that go out and reach, you have two fingers that are effectively conveyor belts and that can convey objects, because you can continually translate the tape along its length. And I'll show some examples of that. The first version of this literally just look like two tape measures. We've got a set of motors here that control the arm angles. They can also control the extension. And what we're going to do is reach out, and this is all just in a planar setting, so we're only sort of manipulating in a planar fashion. But reach out and grab this rubber ball. If you squint, you can kind of see that we've drawn some lines along the hemispheres of this ball. And we're going to retract it so we can convey objects. We can rotate objects in the manipulator. And then we can release. And so, like I was saying, these tapes provide both this sort of rigidity that you want for grabbing onto objects and holding them. It provides reconfigurability because the tape can continuously bend along its length, and we can change the location of that bend on demand. And from that, we have these nice properties of, for instance, adaptability to errant like objects that are in the way of reaching. We can reach out and grab objects even with walls in front of them. We can smash these things against walls and recover. Again, I mean, tape measures are so fun to play with. I hope you all appreciate that you can basically just put a kink in them and repeat that constantly. And, I mean, from the perspective of soft robotics, they're inherently safe. They're strong in regions where you want them to be strong. They're weak in regions where you want them to be weak. They produce enough force to manipulate objects, but not to harm anybody. So I think they have a lot of really interesting applications. And in the context of planar manipulation, I think this is really interesting. The other aspect is that this joint right here, what I call this revolute joint, it's effectively a compliance element as well. As you apply forces on the inner side of the tape, that compresses. And so you can get out nice force control from the system using force feedback. We can do really complicated manipulation tasks like twisting a cherry tomato off the vine. And then lots of other examples. They're all going to be twisting because that's one of the, I think, unique examples of using this tape type structure. But you basically, if I had an infinite length of tape, I now have really unique kinematics for manipulation, right? Like we can basically do lots and lots of really interesting twisting-based manipulation. We can also form conveyor belts on the fly. So we can maybe, a lot of our examples are, I don't know, fruits and things like that. They're nice things to manipulate that are relatively soft. You can lift relatively heavy loads. And again, you kind of, if you squint, you can see the compression that's happening within that, the bend of the tape spring. There's a lot of mechanical characterization that went into tape springs, sort of behind the scenes of all of this. I'm just showing you flashy demos because I have a lot of flashy demos that I want to show you throughout the day. And lastly, the kinematics of this are relatively simple. It's basically just two triangles with a length constraint, and then you can change that overall length. And so, all of this is done by the student who built this, basically just driving it around with a joystick and grabbing objects and doing all the kind of demos that I just showed. Awesome. So, that's sort of like two examples that I wanted to just show of where I find compliance in mechanical structures to be really fascinating, and the ability to control that compliance, locate that compliance where you would want to within the body of a robot, to provide really interesting opportunities for locomotion and manipulation. There's no dynamics at the heart of really anything that I've shown you so far. Everything is just manipulating the structure of the robot. Yet that still allows for interesting kind of interactions with the world that might be unintended or unexpected, and the sort of adaptivity coming through the compliant structure of the robot itself. I want to move on now to something completely different, and I apologize for that. Giving you a tour of the breadth of the things that we think about in my lab, and fun different research. Again, all in this theme, I think of adaptivity and dynamics. But I want to talk about the wing beat of insects. So tape springs to insects. This is work that's a collaboration with Dr. Simon Sponberg at Georgia Tech. A lot of this work just recently appeared in Nature in October earlier this year, so we're very excited about that. But I want to talk about how insects generate wing beats, and I'll tie this back into robotics shortly. Insects have elastic elements within their body. When we build flapping wing robots, we often embed springs in them to try and reduce the power cost of flight by using sort of harnessing the resonance of the spring mass dynamics. And so if you write down just a simple spring mass equation that might describe a flapping wing system, you've got a force coming from a motor or a muscle, and then there's inertial torques, aerodynamic torques, and elastic torques all acting about the wing hinge right here. And so this is just a simple harmonic oscillator, if you want to think about it that way. It's a simple second order system just describing a resonant-like system. This is not particularly that new or exciting, but something that I want us to think about for a second is just how insects and how robots generate that flapping wing motion. In the biological world, there's two ways in which wing beats are generated. The first is what's called a synchronous method. And the synchronous method, if I look at the time trace of the wing motion, which is oscillating back and forth, every time the wing oscillates through an oscillation cycle, a muscle got a signal from the brain to say contract, okay? So the muscle is getting a time periodic signal, causing it to contract in an oscillatory fashion. That's causing the wings to oscillate back and forth. This is like equivalent to just driving, a motor joint with a sinusoidal signal and feed forward, and you just have some non-autonomous, time-dependent system that's being actuated. And lots of insects that flap their wings at sort of slow speeds use this what's called synchronous drive. But there's a huge class of insects that use what's called asynchronous drive. Asynchronous means that for many of the cycles of the wing beat, or many periods of wing beat, there's only a few instances where the muscle is actually receiving a signal from the brain or from really like the thoracic ganglia. In most of the periods of oscillation, the wing is oscillating based on a specific stretch property of the muscle itself that's causing it to oscillate in an autonomous fashion. Meaning you don't have signals that are telling this wing to oscillate at a particular frequency. Instead, the feedback from a muscle being stretched and then a particular response of the muscle to that stretch causing it to activate yields truly asynchronous autonomous oscillations of the wing beat. And many insects that flap their wings at high speed use this kind of like asynchronous actuation. So mosquitoes can flap their wings at like 700 hertz, and throughout that time in 700 hertz flapping, maybe every 10 to 20 periods, the brain is doing anything. And when I say the brain, it's sort of really all the brain is doing is just resupplying some energy by supplying a muscle action potential that then allows for calcium to flow into the muscle. The brain isn't even actuating the muscle. It's just sort of keeping the energy supply at the right level. And this method of generating wing beats, is very broad. And because it is truly an autonomous sort of non-time dependent driven system, we think has really unique, interesting adaptive properties. And I'll say these properties are largely unexplored in the biomechanical literature and not really explored in the robotics literature as well. And so, we have this description of the body of an insect, and this description completely applies to the mechanics of a flapping wing robot as well. You've got your elastic spring, your inertial dynamics of the wing, and the aerodynamic forces on the wing as well. But how do we describe the actuation from the muscle in these kind of asynchronous systems? And so what we have known from the biological literature from a long time is that if you take one of these muscles out of an insect and you put it between, let's say, a displacement control, and I apply a step impulse in terms of displacement, so I instantaneously stretch it, what you see is that there's a very quick force response right here from the muscle. And then there's a slow rise in tension and then a decay in that tension. And this slow rise right here, okay, so again, step impulse or step input, a velocity impulse is provided. You have some quick force, but then you've got a slower increase in force and then a decay in force. This property of the muscle has been called delayed stretch activation. And what that means is exactly what I say here. When there's a velocity input to a muscle, there is a phase lag, time lag of the force response, and it increases over time. My picture of this is kind of the following. If this time lag is extremely small, if the sort of rate of response of the muscle is very fast, then the muscle is just a viscous damper. So if I apply a velocity, a stretch at constant velocity, I get a force that resists that constant velocity stretch that's proportional to the velocity, just like a viscous damper. Now, what happens if instead I take the velocity that I'm applying and I pass it through a low pass filter, and then I generate a force that's low pass filtered version of that velocity? That's effectively what the muscle is doing here. And this dynamical description of the muscle is just effectively doing system identification on these experiments that biomechanists, neuroscientists have done for a long time. So delayed stretch activation is just this action of basically taking a muscle experiences a stretch. That stretch comes from the antagonistic muscle. In insects, you have sort of pairs of muscles that cause these things to oscillate back and forth. And so one muscle stretches the other one, which then actuates, and then it stretches the other one, which actuates, and then stretches the other one, that actuates, and you get this self-sustained oscillation cycle. And so our question was, if we can now understand the dynamics of the muscle from this simple representation that's rooted in these biomechanics experiments, we now have this closed system where we've got the body mechanics described by spring-like dynamics. We've got the muscle that is described by delayed stretch activation. And we were curious if this provided any interesting properties for actuating flapping wing systems, and also just what are the fundamental dynamics of this system. If you look at it and squint, it's a relatively simple system. This FDSA here is the dynamics of the muscle, second order. The input to that is the velocity of the wing, and that FDSA comes up here. This really should say FDSA, I'm sorry about that. But the force that is generated through these second order dynamics then forces the spring mass dynamics of the wing. The motion of the wing then feeds back into the dynamics of the muscle. It's just a coupled second order differential equation. There's only a single nonlinear term. It's like relatively easy to analyze. And so we asked a simple question: when does this admit limit cycle solutions? And the control parameters in the system are just what is that rate of delay, which is captured by this R3 term here. And what is the magnitude of that response? How much does the muscle tension increase as you have a velocity input? And you see a very simple sort of regime of stable and unstable oscillations here. This is just showing the magnitude of the eigenvalues associated with the stability of the origin of this system. And so red just means that the system is going to oscillate and generate a limit cycle. Blue means the system is not going to oscillate and wing beats are not going to emerge. And you can see then insects and us as roboticists have now a nice little control space where we can, by modulating either the time scale of the rate of delayed stretch activation or modulating the magnitude of this tension response, we can cause a system to oscillate or not oscillate. We can turn on wing beats, we can turn them off. And the beautiful thing about this is that the frequency that the system is going to oscillate at is completely just determined by whatever the interaction dynamics of that spring mass system are with the external environment, what its own natural frequency is, whether it collides with things, et cetera, et cetera. So that's what we wanted to explore. We did this in a large scale version where we create basically through a torque controlled motor that has a little spring, torsional spring acting like a thorax here. We can create these kind of like second order dynamics of the body of an insect or of a flapping wing robot. And we can study this process. And so the first thing we did was basically just implement this delayed stretch activation forcing in our motor just in real-time feedback. And I'll show you just the process of basically undergoing this instability here. So here's an example of the motion of a wing where the parameters are small in terms of the magnitude of this response, and the delayed stretch activation doesn't result in limit cycle actuation. As we go up further, you see that a little perturbation to the wing persists a little bit. And as we cross this boundary here, you see that you get these nice oscillations of the wing beat. So this is, fundamentally at the heart of what's going on in flies and bees and mosquitoes and things like that, is that they're crossing some kind of instability when they start to generate wing beats. The wing beats are generated through this closed autonomous system without any time-dependent forcing. And the wing beats then have these nice adaptive properties. The way we looked at these adaptive properties, we looked at it in two specific cases. The first one is what happens when the body mechanics of the system change. So you can do that in experiment by changing the wing inertia. You can change the size and shape of the wing. People in biology have done this by clipping insect wings. As nasty as it may sound, it's one of the nicer things that people do to insects in terms of neuroscience research. But if you just instantaneously change the mechanical properties of the system, what you'll see is that the amplitude and wing beat frequency change relatively quickly. And they change just based on a very simple model of just changing the resonant frequency. The adaptive oscillator, that is the delayed stretch activation component, tracks that change in resonant frequency. Here just shows a couple of experiments changing the system inertia, and you see the frequency goes down, the amplitude goes up. If we rescale this just in terms of 1 over the natural frequency squared, you can see that by changing wing inertia, we're basically just tracking along this line. This delayed stretch activation is just immediately tracking what the new resonant frequency of the flapping wing system is. This is quite nice because I worked for 3 years trying to make robobees fly, and one of the most painful points is that no two robobees are the same. And so you build it, and then you need to figure out what the exact frequency to drive it at is. You try and create it as sharp a resonant peak as you possibly can. So 110 hertz is different from 111 hertz. And you basically have to go in and you have to figure out exactly what frequency you want to drive that robobee at. This kind of actuation just alleviates all that. You just turn it on and it immediately tracks what the natural frequency of the system is, right? Through just setting up the dynamics appropriately so that the system emerges and oscillates at the characteristic frequency of the system. This also tracks experiments done in the 60s of clipping wings, and this is just plotting the exact same thing, 1 over frequency squared, moment of wing inertia, and that's just bumblebee data showing sort of the same effect, that we think this is what's causing all the kind of adaptive responses that you see in insect flight as their wings wear over time, or as they change in sort of body mechanics and stiffness. The wing beat frequencies are tracking kind of the dynamics of this closed system. Excuse me. Please.
And it makes a lot of sense if you thought you could produce the force profile in the material itself. That seems very advantageous.
Yeah.
If you're doing it in the motor, wouldn't you be just as well to do, instead of a 4-dimensional thing, just use a traditional 2-dimensional limit cycle oscillator? You can do that.
Yeah,
it seems much more easily and much more adaptive.
Why use delayed stretch activation? Just use something that's a simpler representation of feedback. Yeah, absolutely. Yeah. No, I think that's a great question. I mean, the examples that I show and the examples that I would show later are all just, we're emulating all of that unique properties of the muscle. We don't yet have a material that can respond like that. We are working with material scientists to try and create this. And that's, I think, something that's very exciting, is to truly get that delayed stretch activation idea embedded into a material. But what I would say is, for the examples that I'm showing here, they're more in service to the biologist than they are to the roboticist. And so if you want to do this, you can achieve the same phenomenon in many different ways. I should also say, I mean, I'm not by any means the first person to look at adaptive oscillators in the context of robotics. I mean, many tens and 20s of years of people looking at these things. And so, yeah, no, I totally agree. You could do this in a much simpler way. Is there anything interesting about this particular structure? I mean, I think that, if you simplify the dynamics and made, instead of just having a delayed stretch activation, but you could think about just having a negative viscosity as your forcing term. So basically just driving you away from the origin. That perfectly well works. However, you have to change that gain knob to make this thing undergo your instability. Maybe there's some challenges with that. And then with the rate controls that you have in delayed stretch activation, you can modulate the wing beat frequency, or you can choose it to track a different like system natural frequency, which is the combination of the body dynamics as well as the actuation dynamics. I don't know. That's kind of a poor argument for why this. I think it's more in service for understanding the biological system. But I think the general idea of using autonomous generation of wing beats is really, really interesting, and I think it provides a lot of cool opportunities. Again, by being able to track the system dynamics just inherently through setting up this this system. The other one is just looking at wing collisions, and so this is work that I did at Harvard with Andrew Mountcastle, looking at wing collisions. There's a wire here. This bee is flapping its wings at about 180 hertz, and it hits a wire, and within about 3 wing beats, it stops its wing beat. That's extremely hard to do in the context, or at least I'm going to claim in the context of sensory feedback loop in a biological system where you have neural latencies and things like that. But it's relatively easy to do if all you're doing is suppressing the stretch of the next muscle. Because again, this actuation is generated by muscles causing themselves to stretch. And so in this dynamic system, we can also study what the response of this delayed stretch activation is to collisions. And the result is that basically these wings will flap at high amplitude and high velocity. And if you hit them and they make them stop moving, they'll stop instantaneously. And they do that without, I'll say without sensors on the wings. They're still monitoring the motion of the motor and generating feedback dependent torques and things like that. But we're not, from my perspective, actively thinking about whether we've hit something or not. It's just we've set up the dynamic structure of the actuation such that collisions cause this thing to halt.
Do we know where this generator of these periodic signals is located?
Yeah, it's a great question. So the generator of the periodic signals.
I'm interested in the innate stuff, because that's really where, if we really want to build axiomatic systems of these systems, we better know what the assumptions are.
Yeah, it's a fantastic question, right? I think that people often look towards like central pattern generators and things like that in biology as the units that produce this oscillation. That's not what is involved here. Instead, it's purely the physical response, the mechanical response of the muscle that as you stretch it under some time delay, it contracts.
Comes from.
There's no signal. That's the.
So where is that generator?
Well, I would say in this context, there's no signal that's generating this oscillation. It's the mechanical stretch response of the muscle itself.
Well, there are several periodic things happening in our body, like as we breathe, as the heart is controlled.
Absolutely, yeah.
Professor Pavlidis, many years ago, from Berkeley, his thesis was that he found one clock where it generates, but there are several others, so I'm puzzled.
Well, and that's what I think is so fun about this, is that there's beautiful work from lampreys, from insects, looking at like the interconnections between central pattern generators along the spine that generate rhythmic motion, right? And there's just, I mean, a vast literature and also examples in using this in robotics. And what I would say is this is sort of different from that in the sense that there's no central pattern generator generating this oscillatory behavior. There's no neural signal that is generating oscillatory actuation of the muscle. The muscle has a mechanical stretch response. And so you can take the muscle out of the body. There's no nervous system that's connected to it. And I can pull on it and it will pull back. And if I connect two of them together, and people in the 1960s, there's these beautiful experiments. People used all analog circuits. They took a muscle, they connected it to a resonator, a spring. They could measure the motion of that spring, and they could then emulate the action of a muscle pulling on a spring mass system, and it would oscillate. They could control the frequency of oscillation. So you can take the muscle out of the body and remove the nervous system entirely, and you get spontaneous oscillations. And that's just what like appeals to me so much, is that you can kind of forget about what the nervous system is doing. Now that's a gross abstraction, right? Because underlying all this is, I mean, the nervous system is controlling the wing hinge, the stiffness of the thorax. They're doing like on a wing beat to wing beat, insects are still doing flight control. They're modulating their wing pitch and things like that. But the drive that's doing the wing beat generation is coming from the mechanics of the muscle. I find it to be really fun and really interesting. So we get, this response here. You halt the wing, it stops oscillating, and you get very interesting and kind of unique properties from this that I think are just like, have a lot of opportunity for making kind of adaptive, sort of inherently responsive flapping wing systems. We've been working on embedding actuation and sensing into the actuators themselves, right? This is all kind of like a proprioceptive type feedback where basically the muscle is just watching its own stretch and then applying forces. All of this can be emulated in very simple analog circuitry, ideally embedded in the mechanics itself. And I think that's really where this would be interesting. If we're just emulating this response, then why not use other forms of actuation? And so we've got a lot of different platforms that we've been kind of playing around with how to embed these kind of feedback properties into. But this kind of delayed stretch activation provides a really interesting form of actuating these systems and allowing for kind of responsive and dynamic behaviors. Like I said, this was a collaboration. It's been a beautiful 7-year collaboration with Simon Sponberg here and a bunch of folks from his lab as well. I'm going to switch gears completely. Sorry. So just 3 pieces of the pie. I want to just, in my last section, talk about how we can make systems that are separate and that don't communicate with each other through electrical communication synchronize their movement. This is a simulation of a Newton's cradle. It like never ends. It just goes forever. Anybody played with a Newton's cradle and watch what happens after a while? They all swing together, right? They're only interacting through contact. Through that contact, they exchange energy, they lose some energy. Eventually, they all end up moving together from any initial condition, okay? I came across this problem from work that it was actually done here at Penn, looking at worms swimming in a tube. These are C. elegans worms. They put them in a pipette and they found that when they're separated, they swim at different phase offsets, and when they come together, they swim at the same phase. So they synchronize their gaits by swimming. They did all these like genetic knockouts and things like that to remove touch sensing, to remove any kind of like chemical sensing. The worms don't know that another worm is there. They always synchronize their gaits. And the thing that stuck out to me in this paper is this word right here, steric hindrance. Steric hindrance is just a fancy way of saying contact, that the interactions are happening purely through contact. There's no fluid mechanics involved in the problem. And they don't know that they're touching another worm through like special touch sensors or tactile sensors. And the other thing that I knew about C. elegans worms is that the way that they generate their periodic gait is through local proprioceptive feedback along the body. Okay, so they've got these stretch sensors along the body. When one muscle contracts, it stretches, then the descending proprioceptive circuit a little bit down further the body feels this stretch, it then actuates, and you get this propagating wave down the body. And you got this kind of reflex chain of actuation. And this led me to think this combination of generation of undulatory gaits that are purely just through local feedback within the body and contact interactions, and only contact interactions, might yield some interesting opportunities for robotics to synchronize their behavior without communication. So very specifically, without ever talking to each other whatsoever. If anybody's searched synchrony or done any sort of very basic nonlinear dynamic studies, there's, I mean, a million papers on synchrony. Sort of like when you look at it long enough, it's not that interesting. But critically, lots of examples of hybridynamics, especially some done here, lots done here. And so I want to just kind of like give you the picture of the problem that we were looking at, inspired by this worm swimming. And the problem looks like the following. Imagine that you have just the generation of 2 oscillatory movements. The most simple example of that is just literally the harmonic oscillator. We can track the movement of, or the dynamics of a harmonic oscillator by just following the phase of it in phase space with position and velocity. And 2 harmonic oscillators will just evolve with a constant phase rate and just do this forever and ever and ever. And it's sort of uninteresting. But the sort of canonical case that we're interested in is what happens when they interact through contact. So a harmonic oscillator, 2 spring masses, and this is kind of the equivalent of like a Newton's cradle, when they interact through some inelastic collision, what you can see is that their phases are eventually going to come into sync. They've lost some amplitude through energy exchange, but you can show that they will always come into synchrony here And the rate at which they come into synchrony is just dependent on the coefficient of restitution. And if you make that coefficient of restitution greater than 1, they'll go into antiphase synchronization. Who pushes the first? I mean, I push the button to let them go, I guess. And then they only just hit each other and they lose a little bit of energy, and then they bounce back and are always just described by simple spring mass dynamics. So you can track this and you can show very simply that they'll synchronize. The case of these worms, though, are that they're an active system, right? So they're not decreasing in amplitude. They're able to generate internal energy and try and track, not track, but try and evolve to some internal limit cycle that their system is sort of at equilibrium with. And so we wanted to study basically this process of what happens when we set up 2 of these autonomous gate undulatory systems that interact purely through contact. And again, I said I've never taken a mechanical engineering class, but I've taken a lot of physics. And so we think about things as like a robot is literally just a motor with a single link, okay? So my worms just look like just a single joint. And I'm gonna cause these joints to oscillate on a limit cycle, and I'm gonna allow them to interact just through purely repulsive contact. We set up the limit cycles kind of far away, and then we bring them into contact. If my volume was up right now, you could kind of hear this clacking. This was done thousands of times in the lab. It was kind of annoying. But what you see is that these 2 motors end up coming into synchrony. Okay, there's no electrical communication through these motors. They're just purely following a limit cycle, and they're purely interacting just through some inelastic contact. We can measure the coefficient of restitution of that inelastic contact. And what I'm going to argue is that the dynamics are actually really simple in this situation, even though you have complicated contact. The beauty of these limit cycle systems is that for the most part, when they're not in contact, we can just think of them as evolving on their limit cycle. And if I treat this as a very simple phase oscillator, those dynamics are completely easy to understand. At the collision, if I just use a simple inelastic coefficient model of collision, then all I need to do is just track the dynamics from collision to collision. Okay, it's somewhat like creating a return map, but the return map is just the instances of contact. So maybe the return map is like the relative position between the 2 of them is the Poincare section, and you construct your return map. And what's nice is in the system, you can actually, under some assumptions of basically just phase dynamics and no radial dynamics, you can build this return map just by pen and paper. It's actually, these are very fun exercises to do. It's a horrible expression, but the only terms that are in this expression, I argue, are just a coefficient of restitution, which is kind of buried in this kappa term, okay? So there's only one thing that this depends on, which is just the coefficient of restitution of the system. If we measure that coefficient of restitution, we can construct the return map. It looks like this. It has a single fixed point here, which is the phase difference of the nth collision and the phase difference of the n+1th collision. And this fixed point here is stable. And then we can measure the experimental data, and it agrees extremely well. And again, the only parameter in this is just coefficient of restitution. That's the only thing that determines what the long time behavior of the system is. Modulating this coefficient of restitution or changing the separation distance will affect this return map, and we have lots of data that shows that it agrees extremely well. But what this showed is that we can achieve simple synchronous behavior in my robot, which is just, again, 2 joint link combinations. They're not talking to each other. They're just interacting through contact. But we set up the gates in the appropriate way that they're generated through this autonomous feedback. So can we actually use this for any kind of interesting robot? That's the next question. So the first thing we did was build our worms, which are just 3-link robots now. Okay, they can generate undulatory gates. And now we just measure the phase error of each joint. If a joint is oscillating without any contact, then its phase error should be 0. If it's in contact with something, its phase error is going to be non-zero. And we just apply basically a simple coefficient or gain coefficient on the phase dynamics of the gate generation. And critically, this is just like what's happening in the robot itself. It's just got some phase oscillator that is slowed down if there's joint error. The motors are just controlled. They're just servos, so they're just controlled in position control. But critically, we can vary this adaptive gain term. And you'll see here that when we set it to be the appropriate value, we can make these robots synchronize extremely quickly. When we make it less than 0, then they're sort of repelled from each other. And as you vary this from 0 to 1, the rate of synchronization goes up the stability of that synchronization changes. And all this, fundamentally at the heart of all of this work, it's just constructing the return map and really constructing the contact-to-contact map and just tuning the functions that vary during that contact. Again, when they're not in contact, all the dynamics are just simple and uncoupled. We did our little worm experiment now. So these robots have a little like snake skin on the bottom of them. They're on a little grass turf here. And again, you'll see they'll synchronize their gaits as they're going through this small channel here. And so, this to me was, I think, good evidence that, these C. elegans worms are just using their own undulatory feedback to generate their internal motion. And just by contacting other worms that happen to be pushing away or pushing towards them cause some phase delays that cause them to synchronize. We can show this, that robots can do this. But I think it presents really interesting opportunities for collectives to interact through contact and to kind of like exchange information, communicate, and coordinate their behaviors. The last example I want to show you is just what if the robots aren't interacting with each other, but they're interacting through a common object, like we're all pushing together. And how do we synchronize ourselves when we might want to push objects? So we played the same game, but we built little simple walking robots. And again, they just evolve as a phase oscillator with some phase rate lags, so slowing down the phase evolution. If they're pushing against something, and again, just controlling them, just these motors truly controlling them through a torque. And so these robots, if I just start them, they're just going to walk. The leg angle plotted here just looks, basically two systems that are just walking and evolving in an uncoupled fashion. But what if I put an object in front of them? If I put an object in front of them, what you'll see is that extremely quickly, they're going to sync up and start pushing together. This is super useful because if you think about pushing with a periodic force, then you push with the most force when your periodic force is aligned. So you can push heavier objects inherently by building in these kinds of responsive dynamics into the robots. And so we set up a system to study this. This is the phase of each of the oscillators in the robots. Robots are pushing this little mass on a trackway. And you can kind of see they all end up pushing together. You can do this in simulation, and it's really robust to the number of robots. You get to play with the kind of amount of feedback that you're invoking and like how you sort of how you take information about that proprioceptive feedback and inform that into the phase evolution. And the same dynamics that I showed for the snakes, we can show in these walking robots as well, that when you have this sort of negative phase feedback, then they're very poor and they all kind of like want to be attracted to an anti-phase synchronization. In the optimal case here, they quickly synchronize their gait, they push an object under constant time, the furthest distance. And so you have this like ability to play in kind of synchrony dynamics purely through interacting through contact. And what's nice is that you only need to pay attention to the dynamics of when they're in contact and just what the evolution of the individual phase is in an instant of contact. And you can analyze that very simply using a lot of the tools that we already know from studying oscillatory systems using Poincare maps. Okay. So I've taken you on a giant tour from starting with structures to flapping wings to collectives that interact through contact. And, at the heart of all of this, like I'm fundamentally just attracted to mechanisms and dynamics that have simplicity to them. I like things that I can grasp, things that I can understand, structures that that have very simple, understandable mechanical properties to them. And I think there's a lot of opportunity for studying these kinds of low-dimensional dynamical systems that have still really complicated behaviors through contact, through structural changes, things like that. With that, I want to thank everybody for attending my talk. I think we have plenty of time for questions. And so thank you very much.
Thank you, Dr. Gravish, for this wonderful talk. So now we will open to Q&A. So if you have any questions in the audience, please raise your hand and I'll hand you the mic. Okay, in that case, I'll ask the first question about the oscillators. It's more of a clarification question, but do those oscillator needs to have the same natural frequencies, or?
It's a great question. So they don't within a certain like regime. So certainly in the walking robots, naturally their frequency varies just because it's a built system. That frequency varies by about 5%. In the annoying clacker system that made a lot of noise and that we first studied, we explicitly varied and we detuned the oscillators. And within about like a 15% variation in frequency, they'll still synchronize. And that's, I think, like I said, synchrony, when you look at it long enough, maybe it's just sort of people tend to want to find it and tend to find it interesting. I think fundamentally one of the most interesting and unique features of synchrony is not when two metronomes of the same frequency synchronize, it's when two metronomes of different frequencies, or when 100 oscillators that have a spread of frequencies sync to a common frequency, right? This is the like fundamental, I think, beautiful result from synchronization. And that still is true in these cases. When you have different frequencies too, you get other weird things like cycles of pushing where they won't necessarily sync into the same pushing phase, but you'll get like these cyclic behaviors of their pushing contact times. Becomes more subtle, but it is relatively robust to, I don't know, 10 to 15% variation in the systems we studied.
Thanks, Nick. So I have a question about the method. So for the case where you built the system to mimic how the wing flaps, is the reproduction of a particular phenomena or behavior a good verification of how it's actually done in biology? So in the worm case, if you do a control experiment by eliminating the senses, and then you realize the dominant factor is contact, I think that makes sense. But then if we build something that can produce a behavior, it's not necessarily true that in biology, that's how it's produced, right? Or how would you think about this question?
No, it's a great question. I mean, I think that like sometimes we tend to overstep our interpretation of like what a physically modeled experiment says about the natural system, about biology. In this case, like what I would say is the feedback phenomena that we're using to actuate that system, truly, we came to it from looking at the experiments on the muscle itself. And so we've sort of integrated into our torque control of the motor our best representation of what the muscle is doing. And so from that perspective, I think then the phenomena that we see later on, I think does a reasonable job of ascribing like the delayed stretch activation is what's causing the adaptive frequency behavior of the insect. But there's always the caveat that like, if I take a wing and there's all sorts of sensory, all sorts of sensors along the wing. Who's to say that doesn't freak them out and they change their wing beat frequency just by themselves? Or who's to say that they have some kind of like, let's say, force feedback on the hinge and they can sense what the aerodynamic forces are. Maybe they're modulating the oscillation based off of that. There's no way that we've ruled that out by any means. And so, yeah, I think the interpretation of how far we can take in the biological system, you have to be careful about that. What I would say is that our physical model, our robots, they reproduce phenomena seen in the biological system in under the most simplest interpretation, that it's the delayed stretch activation that's causing this kind of behavior. Beyond that, I can't say. And there could be, let's give us money to do more experiments and we'll maybe try and answer that question. Yeah.
So it was a super interesting talk. I'm wondering if y'all have started thinking about your tube robots that look very similar to the rigid worms that you had at the end, and what contact would mean for those tube robots if you had a collective of them. Do you expect the results to translate very easily, or are you expecting there to be hurdles in contact with those soft robots? So it feels like a natural application of soft robots in a super interesting direction.
Yeah, totally. No, I think that's a great point. I haven't, in some sense, because like my lab feels a bit compartmentalized. We all talk to each other and we're all friendly, but like we just got like these different research directions. And students, the other sad thing is students graduate and projects die. So yeah. But what I would say is that, so let me just maybe get at this. So the system that I showed with the worms are rigid links with a like dynamixel motor. Okay, so I mean, we're doing as best we can to like do proprioceptive sensing out of this dynamixel motor. But if anybody's tried that with a cheap dynamixel motor, I mean, it's like you're definitely not measuring torque out of that thing, and you're at best, you know, tracking some variation in position. And so what we're doing is we're watching position, and then we're converting that into a phase of the oscillator. If you have your servo motor driving this like flexible column, and now through contact, that column, instead of translating into some reduction in speed of the motor, just buckles the column, I think a lot of things are going to be different in terms of like how well this synchronization process is going to happen. All of the analysis is sort of predicated on contact induces some kind of phase delay of the evolution of the undulatory gait. And that might not be true when you have like soft elements where you have some of that you know, compliance of the body effectively can accommodate the displacements, or rather accommodate the like generation of displacements at the joint that then don't track all the way out. Still, you have a force or torque acting back on the joint, and so you still might see the same thing. But no, I think it's a super interesting question of basically what is the role of passive body mechanics in this kind of like synchronization process. Yeah, thanks.
Thank you for your talk. Super interesting. And I'm more curious about the like bend tape gripper. I think the most demos you make currently is like kind of limited to 2D scenarios. So have you ever thought about doing C3 things? And also like, I think bend tapes are kind of like bistable, right? So the task you show is more like say relatively static tasks. I think when it moves to more like frequently changing or dynamic task, I think, have you ever think about like researching these like kinds of like characteristics in bend tapes? Like,
awesome. Yeah, no, great questions. So far we've only focused on planar manipulators. We've done some examples of having two stacked tapes. So the manipulation sort of workspace is still planar, but the ability to rotate now is three-dimensional because you can translate along 4 points of contact. We are, you know, I kind of like showed this because I'm extremely excited about it, but it's a fairly like new project in the lab. And so I really think three-dimensional manipulation is going to be something very, very interesting to look at. We haven't though. We have, and I didn't show this, built legs out of these systems too, and built walkers that can basically go from this tall to this tall. These tape springs are super strong. And the key to that, I didn't show or didn't talk specifically about it though. If you take a tape spring and you push on it, it'll buckle extremely easily because it's got a weak side that it wants to buckle on. If you take two tape springs and you laminate them together, you've now made a tape spring that has a high tensile load ability. And so we're like not using any of the bistability aspects of the tape spring itself. We preform the buckle, and the buckle is just there. The buckle meaning that's our joint. So when it sort of fails under load, that is like part of the bistability aspect of it, that it fails. Maybe that's nice because you've got like a sort of force diode that you can't exceed a certain load, and it has some inherent protections from that standpoint, but we haven't done anything with that. Thanks.
I have a question here on Zoom from Dr. Markian. He asks, what for the tape spring, have you tried using other materials or band geometries beside actually tape measures?
It's a great question as well. No, but I hope to meet with you soon and wherever the video camera is, and you can tell me about what tape springs I should use. I know we've just like been burning through Amazon tape measures, and I did find something about having it literally be looking like a yellow tape measure to me seemed kind of like it diminished the project. Like I think this has a lot of really interesting manipulation capabilities. I found there's one supplier out there that sells called Story Tape. It's literally tape that has no measure on it, so it's not useful for anything, but it's like useful, I guess, because people then use permanent marker to mark things. So we bought a bunch of that. So we bought a bunch of just clear white tape as tape measure, because then it maybe would make people not laugh at us when we just show like a tape measure manipulating things. I haven't explored other materials as tape springs, and frankly, I don't really have the expertise to fabricate anything myself. So we just use what's available.
I have a question myself. I was wondering if the C. elegans traveling in tube together have any energetic advantages when they synchronize their gates?
I can't say anything about the C. elegans themselves. I can say for the robots, for sure, yeah. Because again, the thing that I find so interesting about these kind of contact synchronization is that, like, if you paid close attention to the simple links that are oscillating back and forth, once they synchronize, they never know the other one is there anymore because they never make contact with each other, right? The case of the harmonic oscillator, the end state is that they are infinitesimally separated and they're just oscillating in perfect synchrony. They don't know that there's another one there, right? And so certainly if I compare having to push against my neighbor to move versus having to push in an exactly compatible gate as my neighbor, it's going to be better to push in a compatible gate. We did some studies where we did, at least in simulation, basically taking 3 links that are driven through just a pure feed-forward time-dependent actuation, and you compress them into a small space and measure what the joint torques they have to generate to keep their gate going. And it's extremely large. And then you switch them over to this phase oscillator-based actuation, and they immediately synchronize, and the contact forces go to 0. Anybody in the back row? They couldn't hear me back there, I guess so.
All right, in that case, please join me in thanking Nick Gravish again. Thank you, Nick, for that very interesting talk. Final announcements before we close. Please tune in next Friday at the same time for our next GRASP on Robotics talk. And you can find all of the details online on the GRASP website. For more information about our upcoming events, you can check out the website or our social media. In addition, there is pizza outside for those of you who want to hang out, talk about the talk, or engage Nick in further discussion.